Force and a current loop in a non-uniform magnetic field. The net force on a current loop in a uniform magnetic field is zero. But what if B is not uniform? Figure shows a square loop of wire that lies in the xy plane. So this is in the xy plane. The loop has corners at 0, 0, 0L, L0, and LL, and carries a constant current I in the clockwise direction. The magnetic field has no x component, but has both y and z components. It is B0 z over L in j hat direction plus B0 y over L in k hat direction, where B0 is a positive constant. Part A, sketch the magnetic field lines in the YZ plane. Okay, so the magnetic field that is given to us is non-uniform, and it is B0, a constant, Z divided by capital L in j hat direction plus B0 y divided by capital L in k hat direction. So what happens if y is equal to z? So if I'm on the y is equal to z line, in this case you can see that the y component of the magnetic field, which is B0z over L, should be equal to the z component, which is B0y over L. So By is equal to Bz. So if I look at the derivative dBz dBy, the slope is equal to 1. So when y is equal to z, the vector, the magnetic field vector, is basically given like this. It makes 45 degrees with y-axis, 45 degrees with z-axis, so that the y component of this magnetic field and z component of this magnetic field are the same. What happens if z is not equal to y? If z is not equal to y, then I'm going to look at the slope of dBz dBy. What is dBz dBy? So you can see that the z component is B0y over L. So if I take the derivative with respect to derivative of this, but this is basically going to be equal to dBz is B0 over L dy, and dBy is B0 over L dz. So this is going to be equal to dy dz. dy dz, or we can say dby dBz is going to be equal to dz dy. So we can make some comments about the slope here. Now what happens if z is greater than y? You can see that the y component, which is proportional to z, this is the y component. You can basically see that this is by j hat plus bz k hat. If z is greater than y, then I must require that the y component of the magnetic field is greater than its z component. If y is greater than z, then I must require that the z component of the magnetic field is greater than the y component. Now look at the region where z is greater than y. So let's say that y is a small value here, and z is a large value. So in that case, if I draw the magnetic field vector for z greater than y, I'm going to require that this vector is closer to the y-axis so that it has a large y component, but it has a small z component. Basically, this is what I'm going to observe here for this vector as I go further in this situation. Z is greater than y, z is greater than y, z is greater than y. Always I'm going to have this vector that's going to be have a y component that is larger than the z component. So this is has a very small z component here. Now z and y components get close to each other whereas z and y approach each other. So that's basically asymptotically going to this one. For y greater than z, the story is the same. Then I require that the z component, bz, should be greater than by. So this has a large z component, but it has a very small y component. So in this region, y is greater than z. So I'm picking this point. For example, this is 1 unit and y is 3 units. You can see that the z component should be 3 times larger, and therefore this vector is closer to the z-axis. And similarly, asymptotically, it will approach a slope of 1 as y and z approach each other. So that's basically the magnetic field line we're going to draw. Okay. So let's move on to part B. Find the magnitude and direction of the magnetic force exerted on each of the sides of the loop by integrating dF is equal to I dl cross B. All right, so I'm looking at this loop of current here. It has 4 sides, 1, 2, 3, and 4. And once again, my magnetic field is given as B is equal to B0 Z over L in J hat direction plus B0 Y over L B0 Y divided by capital L in K hat direction. And when Z is equal to 0, you can see that the magnetic field is B0 Y over L in K hat direction. Why did I say Z is equal to 0? Because here, this is the z-axis coming towards us. You can see that this loop is on the xy plane. So z is equal to 0. Therefore, the magnetic field has this form on the xy plane. The force dF on each length element will be given by I dl cross product with the magnetic field B. So if I look at the first segment, which is going from 0, 0 to 0, L, so from 0, 0 to 0, capital L, what is the dl vector? dl vector is basically this small vector here, which is pointing in the direction of the current, and it has a magnitude dy, right? So this is going to have a magnitude dy. So I can say that dl vector is dy in j hat direction. So what is the force on the first segment then? The force on the first segment will be I integral as y goes from 0 to L dy j hat, which is dl, cross with magnetic field, which is B0 y divided by L k hat. What is j hat cross k hat? If I do these cyclic permutations, j hat cross k hat is I hat. So I note here that j hat cross k hat is I hat. Okay, so this force on the first segment can then be written as I integral from 0 to capital L. J hat cross k hat is I hat. I have B0 y divided by capital L dy in I hat direction, which is I B0 divided by capital L. The integral of y dy is y squared over 2 evaluated between L and 0. This is going to be L squared over 2 in I hat direction. So you can see that one of these L's will disappear, and I will find the force on the first segment to be F1. The first segment is IB0L over 2 in I hat direction. Okay, now let's work on the second segment. Now I'm going from 0L to LL. So from 0 capital L to LL, second segment. What is the dl vector in this case? Well, the dl vector is for this line element, it is basically dx. It has magnitude dx pointing in I hat direction. So this was dy, this is dx. So for this one, I write dl vector is equal to dx in I hat direction. And in this segment, y is equal to L. So the magnetic field is, which is B0 y over L, is B0 in k hat direction. Okay, so force on the second segment, can then be written as I integral as x goes from 0 to L dx I hat cross with B0 k hat. Now the question is, what is I hat cross k hat? I hat cross k hat, I'm going in the negative direction. So basically, if I go in the reverse direction, this is negative. I hat cross k hat is minus j hat. So I hat cross k hat is minus j hat. So this is going to give me then minus I B0 integral of dx is x evaluated between 0 and L, it's L, minus I B0 L in j hat direction. So basically I can write the force on the second segment as minus I B0 L in j hat direction. That's my answer for the second segment. Let's move on to the third segment. What is the third segment? It is going from LL to L0. So going from LL to L0. Now what is my dl vector? dl vector is dy in j hat direction, but here dy is negative because I'm going in the negative direction, in the direction of decreasing y. So once again, this is going to be my dl vector, which has a magnitude dy. Okay, so the force on the third segment then can be written as I integral y goes from capital L to 0 dy j hat, which is my dl vector, cross product with b0 y over L in k hat direction. What is j hat cross k hat? This is going to be j hat cross k hat, which is I hat. So that will give me I b0 over L. The integral of dy from L to 0, dy times y from L to 0 will give me L squared over 2 with a minus sign, because if I evaluate that L first and subtract it from the evaluation at 0, which is 0, it will give me a minus sign. So let's do that here. The integral gives me y squared over 2, which will be evaluated between L and 0. Evaluate that 0 is 0. Evaluate that L is L squared over 2. So 0 minus L squared over 2. This will give me minus IB0L over 2 in I hat direction. Because this L squared over 2 will cancel with this L. All right. So let's keep this answer for the third segment. Force on the third segment is minus I B0L over 2 I hat. Now let's do the final segment, the fourth segment. We're going from x equals L to x equals 0 and y is equal to 0 on the x-axis. Once again, my dl vector is dx in I hat direction. So this is my dl vector, which has a magnitude of dx. And x is decreasing, so dx is going to be negative as I decrease the x value. The force on the fourth segment can then be written as I integral from x equals L to x equals 0 dx I hat cross with b0y over L k hat. What is I hat cross k hat? I hat cross k hat is minus j hat. So that I'm going to substitute here. So this will be, because this is being done at y is equal to 0, the magnetic field here is 0. So that integral is being performed at y is equal to 0. So no need to worry about the direction. F on the fourth segment will be equal to 0. 0 in whichever direction you can give here. I hat cross k hat, that's normally it would be in minus j hat direction. But we can write this as identically 0. Okay, so let's move on to part C. Find the magnitude and direction of the net magnetic force on the loop. Well, we have evaluated this force for all segments of the loop, so we can just add up the contributions. The net force on this loop will be the force on the first segment plus the force on the second segment plus the force on the third and the force on the fourth segments. So what did we find for the first segment? We have found IB0L over 2 I hat. So this is IB0L over 2 I hat. Force on the second segment is minus IB0L J hat minus IB0L J hat. Force on the third segment is here, minus IB0L over 2 I hat. So this is minus IB0L over 2 I hat. Now you can see that these two terms will basically cancel. And there is the fourth segment, which is 0. So I find that the net force acting on this current loop is minus I B0L in J hat direction. Okay. So in this problem, we have a non-uniform magnetic field acting on a current loop, and we want to know the force, the net force acting on this loop due to this magnetic field. The magnetic field is given as B0 Z over L J hat, which is going to have a large y component if z is large. So as z gets large, the z is much greater than y. We're going to see a large y component. So here, for example, I pick y is equal to 2, z is equal to 3. This is going to have a large y component, so almost parallel to the y-axis. Now, it's going to be a large z component when y is greater than z, so it's going to be almost vertical here, parallel to the z-axis when y is greater than z. So when y is equal to z, the y and z components are the same, so that it's going to have a slope of 1. So basically, this is how the field lines look. What is the direction and magnitude of the magnetic force exerted on each side of the loop? Well, for the first segment, the dl vector is dyj hat. For the second segment, dxi hat. Third segment, dyj hat. And dy is negative because y is coming down. And here it's dxi hat. dx is negative because x is decreasing. So for the fourth segment here, we see that y is equal to 0, and this is on the xy plane, so z is equal to 0, y is equal to 0. On this fourth segment, the magnetic field is 0. There is no force. The force on the first segment is calculated by I dl cross b. The magnetic field there is b0 y over l k hat. Y varies between 0 to l, so I integral 0 to L dy j hat cross with b0 y over L k hat. What is j hat cross k hat? Using cyclic permutations here, I see j hat cross k hat is I hat. So that gives me IB0 L over 2 I hat. Going from 0L to LL, that means x is changing from 0 to L, y is fixed. If y is fixed at L, then I will have a magnetic field B0 k hat. So dx I hat cross with B0 k hat, I hat cross k hat, I hat cross k hat, that's the negative direction, gives me minus j hat. So minus IB0L j hat. For the third segment, F3, it's very similar to F1, only x is decreasing, so this integral is just, the limits are reversed. So I find minus IB0L over 2 I hat. For the fourth segment, as I said, because the magnetic field there is 0, the force is 0. So the net force is the sum of these four. the first and third segments cancel, and the second segment gives me the net force minus IB0L J hat.